So the next talk we'll be moving on to, we have two talks about future opportunities in the high pressure community at the synchrotron. So the first talk will be given by Mark Rivers from the University of Chicago, titled APS-U New Opportunities for High Pressure Earth Science.
So I'm going to talk today a little bit about the APS upgrade, which you've already heard a little bit about, both in Erjan's talk and Ninad's talk. But I'll talk a little bit more about the details of the upgrade itself and a little bit about what we're planning at Jessicars in the high pressure program to take advantage of the upgrade. So let me start with a couple of slides about the APS today. I think everybody knows this is one of the DOE BES light sources. It's the high energy machine in the US, currently runs at 7 GeV and 100 milliamps, designed to be a high brightness machine with small X-ray beams and good coherence. And as you heard from Erjan, the timing structure of the APS is unique, actually not just in the United States, but with, around the world in machines of this size. So it's got this large few number of bunches in the machine, at least in one of the modes that it runs in, which is really very nice for doing fast time-resolved experiments, not just in earth science, but for example, in structural biology, and also the nuclear resonance experiments that you heard about this morning. Right now, the APS has roughly 68 beam lines. About 2/3 are undulator and a third are bending magnets. And about half are funded by DOE BES out of the base APS budget. And the other half are funded by CATS that Ninad mentioned, funded by a variety of other funding agencies. The APS got its first light in 1996. So it's 25 years ago, and most of the beam lines are approaching 20 years old at least. So, and at the APS, there are a number of beam lines that are used for high pressure geoscience. And in this list here, I've highlighted in red the ones where roughly at least 25% of the station time is for high pressure geoscience, and broken it down by technique. So there's diamond anvil cell diffraction and scattering. On 11 ID, it's mostly PDF. And then on sector 13, you've heard about it today with the PX2 program. We've got the BREWAN program and the multi-anvil in 13 BMT, IDC with the Paris Edinburgh press you just heard about, and in 13 IDD, the 1,000-ton press and the double-sided laser heating program that Vitaly talked about. And then sector 16 has stations on both the bending magnet and the ID. And sector 33 has done some work in high pressure with submicron and three-dimensional diffraction. There are multi-anvil presses that you heard about from Don at 6 BM and 13 ID and 13 BMD. And there's some work, but it's relatively small on emission spectroscopy and RICS at 13, 16, and 20. And then the nuclear resonance and inelastic scattering that you heard about from Erjan today. So the APS upgrade is a project to basically replace the entire storage ring at the APS. It's an $815 million project. Reuses about $1.5 billion of existing infrastructure, and that $815 million is roughly evenly split between replacing the accelerator and enhancements and entirely new beam lines. So the new storage ring is going to reduce the emittance dramatically down to 42 picometers, and it's going to change the energy and the current, and I'll get in that in the next slide. So there are basically, because of the change in energy from 7 to 6 GeV, all the beam lines will be getting new insertion devices because at that energy, we wouldn't be able to cover the same spectral range with our existing undulators. And the new machine will have an increased number of superconducting undulators, which are very good at high energy. And the changes in the undulators and the change in the emittance result in brightness increases up to factors of 500. There'll be 9 new feature beam lines, including 2. Let me see that if I can get my pointer here. 2 here that are going into a new outbuilding, one for an in situ nanoprobe and one for high energy X-ray microscope, which is the program that's been going on at 1ID in 4D diffraction. And then there'll be 15 enhanced and improved beam lines and some work in the computing end, artificial intelligence, and so on. This is similar to a slide that Mohammed showed earlier today, where the APS is currently what's called a double bend achromat. So each sector has 2 bending magnets, and it's the emittance of the machine goes essentially as the number of bending magnets, inversely as the number of bending magnets cubed. So by breaking up these bending magnets into the APS will also have 7, as the ESRF does, and greatly decrease the emittance from that cubic scaling. And the emittance also goes down as the emittance goes down, which is a good thing, as the energy goes down. So lowering the energy to 6 has an advantage there too. So this is what it looks like in a 3D model. Today, these 2 bending magnets here, and then in the future, a much larger number of bending magnets here. Reduces the horizontal emittance by about a factor of 70. And this is what the profile of the electron beam looks like today, and where the emittance is 310 picometers. And this is the profile of the electron beam, almost round, when the emittance is 42 picometers. There's some reduction in the divergence of the beam in the horizontal direction, the opening angle of the X-ray beam, but that's not nearly as dramatic because it's close. In the vertical, it's already basically limited by the diffraction limit of the undulator, and in the horizontal, it's not that far away, and so it doesn't go down that much. Talk a little bit about the timeline. The original plan was to have this shutdown begin in June of 2022, but because of COVID, that's not going to be possible. So it's basically been shifted 10 months. So the shutdown will start on April 17th of 2023. There hasn't been any change in the duration of the shutdown. So it's still scheduled to be 1 year, and beam will come back in April of 2024. But that's, the beam back in the accelerator and beginning to turn beam lines on, and it'll take a few months to commission the beam lines, and how long it takes to commission the beam lines will, of course, depend on how much work was done on that beam line during the dark period. If there's new undulators, if there are new optics, new hutches, that sort of thing. Let me just say a word about what happens, what these reduction in emittance actually turns into for the X-ray beam properties. The first property to be considered is the flux, and that's just the total number of photons in a given wavelength that are coming out of the source, out of the undulator or out of the bending magnet. The other items, the other parameters that go into that is what's the divergence of the beam in which those X-rays are contained. And finally, what is the area of the electron beam source from which those photons are originating? And so we can describe a figure of merit that's called the intensity, which is the flux divided by the solid angle, just the ratio of these two. And that's the figure of merit for a beamline or an experiment when you're not doing focusing. So that might be, for example, a multi-anvil press where you just put a slit in front of the sample and you're not doing any focusing. Then the intensity would be the relevant figure of merit. Brightness is the intensity divided by the source area. And that's the appropriate figure of merit for an experiment or a beamline that is doing focusing, because the size of the source determines how well you can focus the beam on the sample. So in detail with the APS upgrade, as I said, there's a 70-fold reduction in emittance. So today, the electron beam in the straight section has a size, a sigma X, of 280 microns, and that shrinks to 14 microns. As I said, the energy of the machine is going to go from 7 to 6 GeV, and that results, for example, in about a 2 times decrease in flux from the bending magnets at 100 keV. There's also an increase in the ring current from 100 milliamps to 200 milliamps. So there's at least 100-fold increase in the brightness from the undulators. That's mostly due to that decrease in the source size. There's also about at least a 10-fold, up to 30-fold increase in the brightness of the bending magnets, again, due to that decrease in the source size, and also the doubling of the current. And there are modest increases, like 2 to 5, in the flux and in the intensity, mostly due to the increase in the ring current. And of course, in order to take advantage of the decreased electron beam size, detectors mirrors and monochrometers need to be made very much close to perfect. And detectors are going to, if the goal is to put more photons in the same size spot, detectors are going to need to be upgraded to take advantage of that. So here's a plot that shows the brightness of a number of sources. The solid lines are the existing sources today, and the dashed lines are the future sources with the upgrades. And the black is the APS, the blue is NSLS2, and the red is the ALS. So let's look first at the APS undulators. So this is an undulator that's in use at sector 13 today, U33, and this is an undulator we will be getting at Jesse Cars as part of the upgrade, 28 millimeter period, and you see the gain is about a factor of 100 in the brightness of that undulator. If we go to NSLS, this is the damping wiggler that XPD, the beamline that Don talked about, is on. This is a new superconducting wiggler beamline that's being built there, hex beamline, which has significantly higher brightness at high energy than the damping wiggler, and in fact is brighter than an APS undulator today at high energies. The APS bending magnet today is this black line down near the bottom, and that goes up by a factor of, say, 30 at 20 keV and about a factor of 10 at 100 keV. And then finally, there's the ALS. Today, they have a super bend. This is what 1222 is on that Quentin talked about today. And the ALS-U, they're not going to be using superconducting magnets, but they are going to make a much smaller source. So at low energy, there's a gain, and then it crosses at about 40 keV, where it becomes less bright than the super bend today. And you notice that the APS bending magnets, APS-U bending magnets, are brighter than the ALS at all energies, whereas today the ALS is brighter above about 40 keV, or I'm sorry, above 65 keV they cross us. So the advantage of the APS upgrade is it's a machine at high energy, so we can probe things inside buried samples and in high pressure vessels. It's very high brightness, so we can focus it very well. And importantly, it also has very high coherence. And for methods that use the coherence for correlation, like XPCS, that the figure of merit goes actually as the square of the brightness. So those techniques gain by factors of 10 to the 4 to 10 to the 6th. So high pressure geoscience and APS-U, most of the high pressure techniques, but not all of them, employ focusing to achieve small beam sizes. So all of these experiments will gain with APS-U. So you can reduce the spot size by a factor of 10 and have the same flux, or you can put 100 times more flux in a given spot. So some of the things that you've heard about is being able to do terapascals with double stage diamond anvils. But that requires us to get down to, order of 200, 250 nanometer focus. We can do, if we don't try to drive the spatial resolution so much, we can drive the time resolution because we have many more photons. So we can now do dynamic experiments in the diamond cell. And coherent diffraction and coherent imaging are really going to gain. Well, these are techniques that need to be developed for high pressure. There has not been a lot of work on these coherent techniques at high pressure yet. The Jesse Cars has succeeded in getting some of that $815 million to upgrade our beamline. And this is a list of the items. So mirrors for the IDE beamline. This is not the high pressure beamline. This is the X-ray microprobe. So there are 3 items that the APS is going to be procuring for us there. Actually 4 at IDE, but then 2 items, the big KB focusing mirrors and a small KB focusing mirror to go well submicron are going to be provided for the IDD and IDC stations. So we're getting a total of something like 700,000 from this APS upgrade project.
1 minute.
Okay, and for the diamond anvil cell program, we've already seen this figure. One of the things that we want to do are to take advantage of the upgrade. First, we want to get a detector like the one that Mohammed described today, like a 9M Eiger detector. That'll take advantage of the much smaller pixel sizes that are needed for these finely focused beams. Take advantage of the fact that we can now do better experiments in the time domain, and also to be able to do the coherent techniques like coherent X-ray diffraction imaging and X-ray XPCS potentially in the experiments at IDD and at both of the BM stations as well. So in summary, the APS upgrade promises, at least 2 more decades of frontier research at the APS. We welcome new ideas for taking advantage of the APS-U properties. So get in touch if you have an idea where we might be able to help your research. And thank you for your attention.
Okay, thank you, Mark, for the very exciting talk. I can see a very bright future ahead. So is there any questions or comments for Mark?
I see one from Wendy.
Hi, Mark.
Okay.
Thanks for that talk. Maybe this is also just kind of a general question that also would have been from Mohammed, but I was wondering, since ESRF, the EPS went first, were there any kind of surprises or unanticipated challenges or pitfalls that occurred during that upgrade that APS-U could take advantage of or learn from?
I'm not sure if Mohammed should probably speak to that, but it's getting awfully late in France, so I'm not sure he's still here. But I can tell you that the ring commissioned very quickly, and that was a very pleasant surprise. That it's given the APS people, made them optimistic that they're going to be able to come back up more quickly than they might have imagined. And I don't know, I haven't heard about any problems at ESRF, but they tend to be not shared.
So yeah, it seemed like it went really smoothly and ahead of schedule and during COVID. So I was like, oh, it's so easy to completely take out your ring and put something new in it.
Right.
Thank you.
Well, Stanford did did it on a much smaller scale a number of years ago, right?
Yeah.
They did it in less than a year.